So, all right. So, in the last class, we have seen uh, uh, like primitive data types and their representation. When we write programs, like we will be using some objects will be of type one type, and some other objects will be of some other type, and we may do operations involving objects from these different types of data. So when we are doing that, we need to be careful. We need to be careful. And so in C, let's say when you are working with an integer, when we write, let's consider this thing. So let's start with a program. So let's say there is an integer IA, and there is a floating point FA. And then if you have something like and float is equal to 3.14, and FA is and IA is equal to FA, and printf IA equal to %d /n IA. So here, if you compile the code and run the code, what will be printed on the screen? Typecast 1.c. So let's try to get rid of this. So you can see that IA holds the value 3. So here on line number 8, what is happening is, this is what is called as an implicit conversion. Implicit type conversion is happening. Implicit conversion. So the floating point data is getting converted into an integer data. So this is important because what happens is, if you look at the floating point, we know that a floating point number is 4 bytes. Okay. And this is FA, and then this is IA. IA integer is also of 4 bytes. But the representation format of floating point numbers and integers is different. So internally, compiler applies a float to int operation, to translate the binary representation associated with 3.14 into an integral representation of 3, because during this process, the fractional part will be ignored. So a separate float to int operation will be performed. Like for example, if you want to see, let's see, if you just take, although you can see if you say FA is equal, IA is equal to FA, it is not the case that whatever the bit pattern that is present here is simply copied to here. It's no, it has to go through a representation translation, because the representation mechanism that we use, the binary representation that we use for floating point numbers, and the binary representation that we use for integers, it is different. So if you want to see what happens under the hood a bit, so let's see, gcc -g typecast 1.c obj dump minus t minus s a dot out. So if you see here in this code, on line number 414, this is the instruction. There is an instruction which converts. The CVT stands for convert. I'm guessing this SS stands for floating point to SI, I think, to integer type. So there is a instruction execution happens underneath on the processor, which translates the floating point number to integer. Similarly, there are instructions which translate integral representation to floating point representation of numbers. So for example, if you do FA is equal to, instead of IA is equal to FA, if you have FA is equal to IA, then what happens is there will be some instruction CNVT, this is CVT, like if you see CVTT. So here the instruction that is used is this. The instruction that is used, the processor instruction used to convert floating to integer is this particular instruction, but we may use a different instruction such as this in order to convert an integer into a floating point representation. Okay. So CVTTSS is single precision truncation, it looks like. Okay. So we have to be aware, though, that on line number 8, you can see there is a difference between line number 8 and line number 10. In line number 10, there is no loss of information when we promote an integer to a floating point number. But on line number 8, there is a loss of information when we promote a floating point number to integer. And we need to know that this loss of information is all right. There is no problem with it. So one way of documenting the fact that we are fine with mapping the floating point number to integer number with loss of the fractional bit information is by using this, what is called as a typecast operation. So earlier there is a implicit typecasting happening. So now we have what is called as an explicit typecast. So let's say when is this explicit typecast useful? Let's take this case, FA is equal to, so we are trying to divide things. Okay, so you want to divide IA by 2. So IA is equal to, let's say, this is equal to 10, and forget about, we don't need this now. Okay, so this is what we are trying to do. So we want to divide IA, that integer, by some value, and we want to see what that value is. FA is equal to %F. So what will be the value that gets printed? When we run this program, so you can easily guess that the value of FA is 5.0. But on the contrary, if it is equal to, this is equal to 9, and when we compile, what will be the value that gets printed? So the value that gets printed, it will not be 4.5, it is 4, because when we divide one integer by another integer, that the fractional part gets lost. So in order to take care of this problem, so what we can do is when we can make this into when we apply this unary operator, this float I presume. So let's put the parenthesis here. So there is an operand here, and that operand initially ia is an integer. You typecast that ia into a floating point number, and now what happens is if you compile this code, then and run it, you get the value as 4.5. So here we are using an explicit typecast operation. So if we draw an expression tree for this, this is what happens. So there is a division operator, and in this division operator, so there is float is considered as a unary operator. Float, this typecasting is considered as unary operator. Unary operator means there is only one operand is considered as an unary operator in C. Can you give me some examples of unary operators? So can you give me some examples of, yeah, plus plus I, it's a unary operator. Yeah, negation. Yeah. So in the while studying bitwise operators, did you study this one? This tilde? Or minus? So like if we say no, ia is equal to minus fa, so this is a unary operator. I think, did you study this in the bitwise operators? Like for example, if the bit pattern is 1011, if you apply tilde of this, it becomes 0100. It's okay, don't worry about it. That's not the point of this discussion. The point of this discussion is so we have an unary operator. So typecasting is considered as a unary operator. So you take this, you take IA and then you apply this unary operator, and then this is division. The second operand for division is 2. And if you, this is an expression tree, and you have equal to, we have FA. This is the expression tree for this. So if the value of IA is, let's say, as in the previous case, if it is equal to 9, for example, then when we apply floating point operator, it becomes 9.0. And so in computers, the circuitry in your computer, it cannot perform arithmetic between an integer and a floating point number. So what happens is your compiler, internally, you don't know that, internally, it changes this tree, it internally inserts this float operator. So here, so there is an implicit, so here, while this is an explicit conversion introduced by the programmer, behind the scenes, there is an implicit type conversion introduced by the compiler. This is implicit. Why is this implicit? Because if you see the code, this type conversion operator is not present, but the compiler keeps it. All right. And then what it does is, so now when we take 2 and when you convert it into float, it becomes 2.0. So 9.0 divided by 2.0, it is 4.5. And then so this 4.5, so this so we have this equal to, so because, and this gets copied into the memory location associated with FA. Are you all with me here on this one? you have to be careful in certain kinds of type conversions. Like as we have seen, when we try to do a conversion from a float to int, there is a loss of information. Similarly, when you try to convert a long int to an integer, there could be loss of information. Or if you try to convert a short a regular int to a short int, again there could be loss of information. So whenever you are doing operations involving objects from involving variables from different types, you need to know how this type conversion impacts the value of the overall computation that you are doing. Otherwise, you will get into serious errors and you may not realize that. All right. Does this make sense? So just to make it kind of clear, let's say if you are trying to convert an integer which is of 4 bytes into a short integer. Let's say IA is your integer, SIA is your short integer. So if you have something like this, so short SIA. So if we have a statement like this, SIA is equal to IA, so we have to be, you better know what you are doing, because IA is of 4 bytes and SIA is of 2 bytes. So in the copying process, there may be loss of information and should be aware of it. But on the contrary, if we have IA is equal to SIA, it is all right because SIA it's of 2 bytes. And when we promote it to IA, which is of 4 bytes, it should be okay. And now this is about type conversion. So typecasting and type conversion. So there are many rules here. We will not be able to go through them, but whenever you are in doubt, you should refer to the textbook or an appropriate resource to see what you are doing makes semantically correct sense. The next idea is on the next idea uh, is on Typedefs. Short int is correct syntax only. Yeah, we don't need to put int there, so it works, no problem. So the next idea is on creating new data types. You may want to create new data types for various reasons. So the basic data types are there. There is a question, there may be a data loss in int to float also. Why do you think so, Keshav? So I don't think there will be data loss from int to Keshav, but there is a little bit possibility. What can happen is that value, like, so what happens is when we try to represent numbers in float, some of them, they don't have exact representation. Because no, if you think of float or double, so the number of bits are fixed, but the range is infinite. So because of that, yeah, there could be something like 5 could be represented as 4.999999 like that. But let's not worry about it for the time being. You may want to experiment and see how, like, for example, 2 power 31 minus 1 gets represented. That's not an issue because floating point numbers, they can store larger numbers than integers. So the range of floating point numbers is substantially higher than int. So that wouldn't be an issue. So all right, so let's get back here. So when you are working with, so let's say you are working with you are trying to do some writing a program uh, for some bank, and so you may want to use new data types. Like for example, you can say type def long int dollars. So here, and then you can have main so here you are able to define type so here what we are doing is we are defining a new data type called as dollars. And yeah, so wherever we use dollars, what happens is the compilers will go back and look at the typedef definition statement which declared or defined that dollars, and then it will know that amount, the representation that we have to use for amount is long int. So this is how we can have user-defined data types for uh, user-defined data types in the program. So the purpose of this the purpose of the user-defined data types is to make the program more readable. So more than this, many times it is useful. It is used when we are working with structs, as Shantanu already mentioned in the chat box. So, like for example, we can have something like struct car name so dollars savings, right? And then you can say bank underscore record, or I'll say customer underscore record. So now, yeah, so now C1, the variable C1, it is of type customer underscore record. So that means in our program, we should be able to use I hope this will work. Let's say put Keshav. Yeah. So you can see this is something so since Keshav has $100 in his account, he is going to give us all a treat. Chai treat. Anyways, yeah. So you get the picture. So you have typecast and Uh, so you have, yeah, what do I say? So using Typedef, it is possible for us to create new user-defined data types. So this is yet another important idea that I would like you to see. So now, so these are the two things in the other class in section. So with this, actually, the two main ideas that I wanted to discuss in today's class, they are kind of over. I want to keep this class light. We will do full throttle next on Saturday class and cover multiple ideas. But for the time being, for today's session, this is what we have. So while working on this in section 1, we encountered some interesting problems, and I would like to bring those problems to you, and you tell me what's going on there. Yeah. So now, can you take a look at this code? And if we compile this code and execute it, what will be printed on the screen? What will be printed on the screen? What are the sequence of values that will be printed on the screen? 3.14. So 3.14, 3.00 and FP is, I would guess what Pranjal, so this is what Pranjal mentioned. I thought this is expectation. So let's see. So the expected output, this is the expected output, right? So the expected output is FA is 3.14 that gets printed on the screen, and A is 3 because on line number 11, 0.14 gets truncated. And on line number 17, so yeah, so maybe we print 3.000. And yeah, Vitish says there will be garbage on line number 17. So there is a reason to believe why it could print garbage, because IA is an integral representation and we are trying to interpret it as a floating point number. So there could be garbage 3.14, something like that. Okay, this is, and this is 3. So this is either garbage or 3.0, depending upon how the compiler is designed, or and then this will be, the last one will be 3 point, yeah. But then when we compile this code and ran it, this is expectation. When we have something, what in the comments, what I have written, no, if we have something like that, it makes sense, but that's not what we got. GCC, yeah, GCC typecast 2.c. So what happened, the surprising thing is line 1. So this is all right. This is what is expected. So no surprise here. This is also no surprise here. And this is also no surprise here. But line number 17, there is a surprise. How is it that no, the value that 0.14 information is lost, right? So how is it the 3.14 is being printed on line number 17 is the surprise, and we don't have an answer for it. So my question for you is, this is the challenge problem I would like you to take, and I want you to tell uh, and I want you to tell what is happening here. Okay, what is the, is there a, it's not as per our expectation. See, the binary representation for int and float is different, it's all right. But when we assigned FA to IA on line number 11, the 0.14 information is lost, right? So, but what is happening on line 17? We are printing 3.14. What is happening? Do you understand the problem? How many of you understood the problem that we are facing here? So this is the challenge problem. I want you to find out what is going on here. I will copy this code and paste it in the chat box. You can So with this problem, with this challenge problem, I would like to conclude today's lecture, and we will catch up on Saturday. So there are multiple ideas we will be seeing on the Saturday's class. We will start the class sharply on time. No, the compiler may promote int to float, but that information is, there will not be a class tomorrow. It will be just be tut. I want you to solve the problems from the homework. So 3 hours. This is the challenge for you. You should take the OJ problems tomorrow and solve it in 3 hours. Yeah, so you should solve the OJ problems in the 3 hours of lab tomorrow. Yes, that's true. Section A lab exams. So Pranjal got it. No, it's, he's saying no, that 0.14. How is it retrieved? No, Rikhil? That 0.14 is lost, and it is lost. No, so just don't. So I want you to take this code and think, okay? And then we can, yeah, how can IA can have the 0.14 information? It is lost. That is the crux of the problem. I don't know. So I will stop recording here, and